All right, let's dive into a classic computer networking puzzle. This is the kind of thing you see in undergraduate classes all the time, and honestly, it trips up so many people. We're going to deconstruct a really common miscalculation about network delay and get you to the right answer.
So let's just jump right in. The big question is this: how long does a packet actually take to get from one point to another across a network link? Seems simple enough, right? But, the devil's in the details. And that's where the confusion usually starts.
Okay, so here's our setup for the puzzle. We've got host A, that's our sender, trying to get a packet over to host B, our receiver. The connection between them, the link, has a capacity of B bits per second. The packet itself is X bits big. And finally, there's D, the propagation delay. Think of D as just the travel time for a single bit to make the physical journey. Got it? Good.
Now, with those pieces in place, let's look at a solution people often come up with. On the surface, it makes a lot of sense, but we have to ask, does the logic actually hold up under scrutiny?
So here's how that common but flawed line of thinking goes. First they say, it takes a certain amount of time just to push the first bit onto the wire, that's 1 over B. Makes sense. Then, that bit has to travel the distance to host B, which takes D seconds. Okay, but here's where it gets weird. Step 3. The argument says that host B needs another 1 over B seconds just to sense that the bit showed up. Then and only then, the rest of the packet arrives, which takes the remaining time.
So when you add all those pieces together, you end up with this formula. Total time is D plus X over B plus this extra 1 over B. Keep an eye on that extra piece. It's the key to this whole thing.
I mean, it seems pretty logical, doesn't it? It feels like we've accounted for everything, putting the bit on the wire, the travel time, this sensing time, and then the rest of the data. But is it actually correct? What do you think?
All right, let's pull back the curtain. It's time to uncover the hidden flaw in that calculation. We're going to call it the phantom delay because, well, it's a delay that isn't really there at all.
And let's not beat around the bush. That calculation is just plain wrong. If this was your answer on a test, sorry, but you wouldn't be getting full credit.
The source material for this problem just puts it perfectly. It says there is overcounting of time. That extra 1 over B factor, we've added time that doesn't actually exist in the real world.
So here's the absolute heart of the mistake. The receiver does not need an extra moment to sense an arriving bit. The instant the electrical signal for that bit arrives, it's there. It's detectable. That whole sensing time idea, that's our phantom delay. It's an illusion.
So, if that whole step-by-step thing is wrong, what's the right way to think about it? Well, to really get it, we need to picture a packet's true journey. We need to think of it like a pipeline.
And this really shows the difference. See, the flawed logic treats the journey like this series of separate, clunky stops and starts. But the correct logic, the pipeline, sees it for what it is, a continuous, flowing stream of bits. And the result? The last bit gets there at time D plus X over B. We get to completely slash that phantom sensing delay.
Let's walk through the correct timeline step by step. At time 0, host A starts pushing out that very first bit. By time 1 over B, that first bit is now fully on the wire. Now, at time D, the leading edge of that first bit hits host B. And here is the crucial part. The rest of the bits are streaming in right behind it, continuously. The trailing edge of the very last bit arrives at time D plus X over B. And at that moment, bam, the entire packet has been received.
Honestly, the best way to visualize this is to think about water flowing through a pipe. The length of the pipe creates a delay for the first drop to get to the other end. That's our D. And the time it takes for you to pump all the water out of the faucet is X over B. But think about it. Once that first drop arrives, the rest of the water just flows continuously right behind it. You don't wait for each drop to be sensed, right? It's a continuous stream, and the job is done when the very last drop arrives.
So now that we've totally deconstructed that error, let's lock in the core formula so you get this right every single time.
And there it is. Beautifully simple. The total time is just D plus X over B. That's it. Nothing extra, nothing complicated.
Let's just break that down one last time so it really sticks. The first part, D sub D, is the propagation delay. This is pure physics. It's just the time it takes for a signal to physically travel the length of the wire or fiber. It all comes down to distance and the speed of light. And the second part, X over B, is the transmission delay. This has nothing to do with distance. This is all about the sender's hardware. It's the time it takes for the sender to literally push all X bits of the packet onto the link, given its speed, B.
Think of it as how long it takes to get the whole train out of the station.
So it all boils down to this really simple idea. The total time is just the sum of these two different delays. You've got propagation delay for the travel and transmission delay for the sending, and that is the whole story.
Just 2. That is the number to remember. The flawed way tries to trick you into thinking there are 3 things to worry about: transmit, propagate, and that imaginary sense. But that sensing delay is a phantom. In the real world, there are only 2 delays that matter here: propagation and transmission. That's it.
So there you have it. Now you can spot a phantom delay from a mile away and correctly figure out one of the most basic things in networking. And it kind of makes you wonder, right? What other networking truths or things we just assume might actually deserve a second look?